world will never be the same.
In the closing years of the 19th century, the world was entering the electric revolution. In the United States, a fierce contest raged over electric power transmission, the War of the Currents. On one side, Thomas Edison advocated direct current, or DC. On the other, Nikola Tesla and George Westinghouse promoted alternating current, or AC, which could travel long distances more efficiently and was far less hazardous over high-voltage lines.
His current kills people.
By the dawn of the 20th century, AC had prevailed, lighting modern cities worldwide. Although Edison didn't win that battle, his work on the electric light bulb led to an unexpected discovery, one that would ultimately pave the way for the electronics of the future. Out of Edison's humble incandescent lamps appeared a strange phenomenon. When the filament was heated white-hot with direct current, the bulb's interior eventually darkened on one side, as tiny particles from the filament deposited on the glass. Working to address it, Edison observed that a current could pass through a partial vacuum from the hot filament to a nearby metal plate, an effect he filed a patent for in 1883.
Want broad claims on using the current given by heated vacuum lamps for this purpose and other purposes.
Later known as the Edison effect, though he could not foresee its destiny.
I have just completed a pressure indicator which works perfectly.
Following this discovery, engineers began experimenting with the plate's placement and design to better capture the particles and prevent the darkening. This laid the groundwork for the vacuum tube era. In 1906, Lee De Forest added a third electrode, the grid, inventing the triode, the first vacuum tube capable of amplifying electrical signals. By placing a wire mesh grid between the heated cathode and the plate, he could control the flow of electricity, turning faint currents into strong, usable signals. Triodes transformed communication. They gave birth to the modern radio, enabled long-distance telephony, and connected continents. A small change of the grid could regulate a much larger current between cathode and plate, a principle that was truly revolutionary.
Surely you don't wish to hurt your mother.
All I want is the woman I love.
It's time you faced back at the Hotel Oxford in Birmingham, England.
The telephone messages and television programs of a message-hungry world. The electron tube had its...
Yet these early tubes remained fragile, bulky, and power-hungry. By the 1940s, the promise of electronic amplification had grown into something huge. Computers like the electronic numerical integrator and computer relied on tens of thousands of vacuum tubes to perform calculations, filling entire rooms with blinking panels and glowing filaments. These power-hungry machines consumed massive amounts of electricity and required constant maintenance, as tubes frequently burned out or failed. Researchers were searching for something smaller and far more reliable. At Bell Telephone Laboratories, John Bardeen, Walter Brattain, and William Shockley developed a new kind of amplifier, the transistor.
The transistor, operating on a new and different principle arising from basic research on solid substances and how the electrons inside them behave, investigating the surface properties of germanium, a substance known to be a semiconductor of electricity. Their study suggested a way to amplify an electric current within a solid. The transistor was born.
Bell Labs coined the name transistor, combining transconductance and varistor. Other proposed names included the semiconductor triode.
The year, 1947.
In 1947, they unveiled the first working prototype, a PNP point contact transistor made from germanium instead of vacuum tubes.
And this is one of the latest transistors, a much more sophisticated device, but based on the same physical principles as its ancestor. The impact of the transistor on the electronic industry and on our society is unquestioned.
Their transistor worked on a principle similar to the triode. A small input at the transistor's base could control a much larger current flowing between the emitter and collector contacts of the germanium crystal. In essence, the transistor was a solid-state triode. The analogy to the triode's grid made its operation easier to understand. But now it was solid-state, without the heat, bulk, or fragility of vacuum tubes, and without filaments to burn out. The three inventors were later awarded the 1956 Nobel Prize in Physics. The invention of the transistor revolutionized computing. By the late 1950s, transistors had moved beyond the laboratory. Engineers began replacing bulky vacuum tubes with transistors, creating machines that were faster, more compact, and far more reliable. One landmark example was the IBM 7090, a fully transistorized computer introduced in 1959. The IBM 7090 played a crucial role in space exploration. NASA used it to perform the complex calculations needed to plan trajectories and guidance systems for missions that would eventually take humans to the moon.
This is the Goddard Space Flight Center in Greenbelt, Maryland. Through here funnels the voice and teletype communications that link the global stations to Mercury control. The computers enable men to reach judgments within the flashes of time allowed for control of a spacecraft that moves faster than a brain can react. Throughout the flight, the computers will generate recommendations on whether the mission should continue or be aborted. They will determine locations of the spacecraft, the time it should begin re-entry, the point at which it will land. Today is February 20th, 1962. And today, if all goes well, the men here will launch an American astronaut into orbit around the world in a spacecraft which he has named Friendship 7. Friendship 7 awaits its pilot. His name is John Glenn.
All recorders too fast, T-minus 18 seconds and counting engine start.
May the wee ones be with you, Thomas.
Good Lord, ride all the ways.
Godspeed, John Glenn. 10, 9, 8, 7, 6, 5, 4, 3.
Clock is started.
Oh, that view is tremendous.
To John Glenn now belongs an awesome panorama. The world curving beneath him, just as it was filmed from an earlier Mercury capsule.
By the 1960s, transistors had become the foundation of modern electronics. But the transistor's greatest promise lay in its destiny to shrink. Engineers soon learned to carve not one, but millions of transistors into a single piece of silicon semiconductor. From these integrated circuits, the future of computing was born. What began as a quirk in Edison's light bulb now pulses at the heart of every electronic device we use.